All right, I now want to talk about path loss from what you could say is a statistical perspective. And to motivate that is that path loss in the real world can be complicated. We saw that propagation even off of single objects like reflections or diffractions can be relatively complicated to analyze when you get into a real environment with several walls, objects, particularly with motion. This becomes really difficult to analytically understand. Now, there are what you could call site-specific tools, namely things like ray tracing, that can predict the propagation in a particular environment. So as an example, I've shown a couple of outputs of a popular commercial wind prop ray tracer. So in this type of tool, you locate a transmitter, let's say like an access point inside this building, and will predict the signal strength if you give it the 3D geometry of the building along with the characteristics of the materials. But the question is how to generalize that into a typical setting. So if I ask statistically on average, what would the propagation look like in a typical building? And for that, what we need are what you could call statistical models. So in statistical models, what you try to do is model the channel over an ensemble of environments, modeling the channel essentially as a random variable, thinking about all those environmental changes or environmental differences as random. Now, the way you can think about that mathematically in the lingo of machine learning today is as what you would say is a generative model. So you have some, say, link conditions, let's say like the distance that you are from the transmitter and maybe things like the antenna height. And then you think of the output that you're interested in, the channel state, let's say like the path loss or whether the link is in line of sight or non-line of sight. We'll talk about many other attributes for that channel data later. And think of that random variable x as a random function of this link conditions. Or you can think that alternatively is that there's some randomness, which I'll denote by z, and then this x is a function of the link conditions along with that randomness. This type of model where you write x as this random function is in machine learning today called a generative model. Now, what you would do instead of trying to derive this function or this random model from first principles, you typically fit it to data. So you collect a large amount of measurements or maybe data from ray tracing in some type of environment that you're trying to model, maybe urban outdoor scenarios or suburban or urban or something like this, and then try to fit that function based on that data that you have. In essence, you're really, from a mathematical standpoint, trying to fit this function to match that conditional distribution of the x that you're seeing. We're going to go through in the lab. If you finish this unit, you'll actually try to fit some very simple functions from the data, but I'm going to walk you through some examples, just of a few key points right now. Now, what you might ask, what's the purpose of this kind of statistical model? This is often used in a lot of standards bodies to try to estimate the performance of a system. So when you're in the design stage, you have not actually deployed that system in the real world and you're making design choices, and you want to ask yourself the question, well, if I make this design choice, how well will this do? Well, how well it will do will typically vary depending on where the transmitter and receiver are placed, but you can try to get a statistical understanding. For example, say with 90% chance the user will be able to get a megabit per second or some kind of statement like that. Now, the way it works in typical kind of evaluation methodology is you have sort of three parts. Typically, you start off with what you would call a deployment model, and there's some statistical model for the where the users are located, for example, in a cellular system, and where they might be located relative to the base stations. So, for example, you might say that on average, the base stations are a certain distance apart from one another, and on average, the users are located relative to the base station in some manner. And then after this, based on this deployment model, you will what you call drop the base stations and the UEs in some area, and that gives you the locations and the relative distances between the UEs and the base stations. At this point, you will then use your generative channel model that you fit, hopefully, for that environment, and it will generate random instances of the channels between each transmitter and receiver, typically not just between the serving cell, but also the interfering cells. We'll talk much later about how to do a detailed simulation like this when we get later on into the class, but just to understand right now the context of where we're going. Once you have the channels between all the transmitters and receivers, and based on the algorithms that you're using in your modems and the other higher layer protocols, you can then come up with some kind of statistical performance evaluation. Namely that, well, I've run this simulation a dozen or many times, and I've seen that I can get a certain data rate with a certain probability. So all of this type of evaluation we'll return to later, but I just want to quickly talk about what the kind of nature of these generative channel models look like. So one aspect of the channel, and we'll see there are many other aspects, is just trying to model that path loss. So we saw an analytic expression for the path loss in free space, and that has a closed form expression, but of course the real world is in free space. And we mentioned earlier that once you have even very simple things like ground reflections, that path loss becomes quite a bit more complicated. So one way to model it statistically is saying that, well, the path loss will have some function of the distance, and but it will be linear in the log of the distance. So there will be a slope term alpha and an intercept term beta, but then even given the distance, there'll be some randomness, because of course the real world has some randomness depending on the particular locations of obstacles and other variations in the environment. So this term alpha would in some sense correspond something like the path loss exponent that we saw, because it's the logarithmic decay in the distance, plus some offset terms like this. This is a very common type of model, and you can see here how you might fit that to data. So in this case here, we have some data points are measured in both what you would say non-line of sight and line of sight settings, and then we basically try to fit a line. Now, you see in this real world measurements here that there's quite a bit of variability around that line, because if you take two transmitters and receivers, you let they're at the same distance, there could obviously be variabilities depending on whether there are obstacles between the transmitter and receiver. Now, one caution about using any type of model that's fit from data is that you really want to make sure you're using that in the regime where the model was fit, because typically they give you often kind of absurd values if you take it out of those regimes. There are lots of variants of these types of models. One variant is called the close-in model. In that case, you only fit the path loss exponent, and you keep the intercept fixed to the free space path loss at some reference distance, which is typically about 1 meter. And there's other models that you can look up in various texts. I'm not going to go through them here. Maybe I'll have you, actually in the lab, you'll look at one particular example for indoor propagation in indoor propagation from a 3GPP model. All right, just to give you a kind of hint of the kinds of things you can do with a statistical model is look at outage probability. I'm going to return to this later on when we think about link adaptation, but just give you a kind of hint about what's the use of these things. So just for simplicity, imagine you have transmission with a fixed modulation coding scheme with a rate R, so there's no adaptation. So this might happen, for example, if it's a broadcast medium where there's no possible feedback channel from the receiver. And let's just say, because it's at a fixed MCS, we need that the SNR to be greater than some minimum SNR for this transmission to get through. And if it's greater than that, you'll get your rate R. If it's less than that, you'll get 0 rate because it will fail. Now, let's say that I have some statistical model for the SNR, so the SNR is some random variable. I can then compute what you would say is the outage probability, which is the probability that the SNR is less than the minimum SNR. But the SNR is just going to be my transmit power minus the path loss minus the power of the noise. And then if I have this as a random variable, I can then compute that, and I'll have you do some exercises just to get you comfortable with that. So on that note, go ahead at the end of this section. There's a simple little in-class exercise here. I've created a very, very simple statistical model where the channel between one of two states, a line of sight state and a non-line of sight state, and I have some statistical simple description for both of those states, and then you're just going to just do a quick simulation to get an idea of the distribution of the path loss, and then you can do some simple computations with that.